Hi all, welcome to yet another episode of Theoretically Podcasting. Today, I woke up in the morning realizing that I have yet again failed to organize a guest for the podcast, and so it's going to be another solo episode. I thought that I would use as inspiration the following article that came out last night by my friends Amr Ahmadian and Aaron Wall over at Cambridge, titled Off-Shell Strings 1, S-Matrix in Action. So there's a promise for part 2 as well. I was aware of this work from having talked to Aaron while I was visiting Cambridge, and I eagerly awaited the posting of this article. Now, although I started off like this, it wasn't my intention to actually review the paper because I would much rather have Amr or Aaron actually on the podcast to talk to about this. But I thought that I could provide a little bit of foreground, a little bit of a trailer, just based on some of the field theoretic concepts that appear in this work. So their main motivation is explaining why Zeitlin's off-shell formulation string theory is well defined, and they comment on subtleties associated with the killing group SL2C of the sphere. They control that and show how Zeitlin's sphere prescription recovers the standard S matrix, and they show how to extract the I epsilon prescription from the UV cutoff on the world sheet. And also, they show that the correct tree-level equations of motion are obtained to all orders in perturbation theory in GS and alpha prime. And finally, they say that they illuminate the close connection between the string action and the C theorem. And it's one of those things that's rather beautiful, and for the wise amongst my audience, is a rather obvious consequence of the machinery of string theory. But to me, it always felt like a very cool thing where there's this intimate connection between the renormalization group of some two-dimensional model, the consistency condition of it, and the equations of motion in some target space. And then if you try to formulate the question of, well, what is the associated object in the renormalization group perspective of the two-dimensional theory that then maps onto what we would think of as the effective action in the bulk or in the target space? The answer ends up being this C function, which is C away from criticality. This was an object that was used by Zamolodchikov to prove that C is monotonic under the IG flow, and basically to prove a strong version of this, where it was not only showed that the C central charge of the UV conformal field theory is larger than the central charge of the IR conformal field theory when there's an RG flow running between them, but also that there's an object in the middle, so to speak, along the RG flow that decreases monotonically. Now, I won't cover Zamolodchikov's original argument, which is done in many very nice references, and of course his papers about this topic are also very interesting. But instead, what I thought I would do is go over the following work by Osborne about the so-called local renormalization group, which provides yet another view into the strong C theorem, specifically into the monotonicity argument, that I always found very pretty. Now, this is a little bit of cult literature because there aren't that many people that are familiar with this formalism. And again, the wise amongst my audience would probably find this somewhat obvious as to why it should work. But I found it to be very pretty and very, very beautiful when I first encountered it. And I thought that I would do a very brief podcast today describing the mechanics of Osborne's local RG and how you get to the C theorem through it. So I'll lay out just conventions here, and then we can jump back to that very nice paper. So first, the idea is we want to consider the generating function of a quantum field theory as a function of sources, including the metric source, say for some scalar operator, currents, and so on. So there's some list of sources, and these sources are all dependent on space. Now, the actual computation of this object is well, usually very taxing, beyond reach, especially in some arbitrary quantum field theory away from a critical point. But at a fixed point, right, of the renormalization group, as in when we have a CFT, this isn't an altogether unfamiliar object, or the uses of it aren't. In particular, if we take WCFT and just focus on its dependence on the metric, then we're familiar with the fact that the conformal anomaly can be extracted by asking what the response of this generating function is. So I'll just stick to 2 dimensions, keeping with the motivation of one day connecting to what Amr and Aaron are doing. So the basic point is that there's a quantity we compute, which is the response of the generating function to an infinitesimal Weyl transformation. Right, so I should mention that this is log z, partition function, which now depends on the metric ji and so on. Okay. Now, in a CFT, we find 2 dimensions is that we have the following nice relation, right? So we have a C over 24 here, C being the central charge. Not sure about pi's. Apologize for getting it wrong if I am. Anyway, point of saying this is that we already see that even if we cannot typically compute this quantity in closed form, we do know what its variations are under infinitesimal Weyl transformations, say, or under other transformations such as diffeomorphisms, which would give us the translation word identity, and so forth. So what we're really using is the fact that we have relations of the form the expectation value, say the 1-point function of some operator is really given by taking the source variation of our effective action. But note that this is really the 1-point function in the presence of sources, which means that were I to take yet another derivative of this with respect to the source, I would generate a 2-point function and so forth. So this is a much less innocuous object than what we're used to, which is to study, say, 1-point functions in a CFT on the half plane or in whatever setting where we have some fixed backgrounds. So implicitly in a lot of what I'm going to do in what follows, we're going to have correlation functions in the presence of sources, and I'll explicitly mention when that's not the case. And very similarly, we have the other famous relation that tells us that when we compute the metric variation, well, let me lower the indices for now, that what we're defining is really the, there's always going to be a 1 over square root g if I'm not wrong. I suspect that that's the way the definitions work, but never mind. So what we compute is a 1-point function of the integer momentum tensor, again in the presence of sources. And here we see that this equation is just an equation for the trace of the expectation value of the integer momentum tensor. And what's more, because of how we're defining all of this, specifically correlation functions in the presence of sources, these equations hold within correlation functions up to contact terms. So that's how we should see these definitions. Great. So I've missed a factor of sigma here. So sigma is the Weyl factor, right? Great. Now, this equation is going to be important because it will be the template for what Osborne studies away from the fixed point. So this is the only source of the violation of scale invariance when we put the CFD on some general background metric. And, well, if we, for instance, in addition to this, looked at the variation with respect to some sources, we would also see a contribution to the anomaly coming from just the sources of some scalars, for instance. But more generally, if we're just away from the critical point, then what happens is that in response to the variation under Weyl transformations, this the generating function doesn't just produce the anomaly terms. There will certainly be anomaly type terms that don't involve the expectation value of any other operator, but there will also famously be terms that take the following form. So we have that's G sigma. We'll have beta functions, which are now really functions on space through their dependence on the sources. And these beta functions will multiply the expectation values of the operators O to which they couple. So I suppose I should lower the index of I here on the beta function if I wanted to raise it here. Right, so you have a variation like this, and the reason you get this is because you're really taking beta I times delta ji of W. In other words, the variation of interest is really the difference between the infinitesimal Weyl variation and the variation of the source. So you see, like, we have a definition of the beta function as being the sort of change in the source under Weyl transformation times the functional variation of the effective action with respect to the source. So there's some chain rule at play here. And this gives rise to the rest. So you see there's actually some operatorial dependence here. Let me just start by having the metric and the sources of some scalars. The generalization to currents is tedious, but works with the same logic. So now what you're going to have is some set of terms that don't depend on the operators anymore, meaning no more dependence on the derivatives W with respect to either G or J. Right, so here's the derivative with respect to G, right? This defines the trace of the energy momentum tensor. This defines beta times the expectation value, the one-point function of O. And here we're going to have the analog of the anomaly, but it's going to be dressed by other terms. Specifically, in a certain power counting scheme, and there will be comment on what the choices are here in choosing these terms, but what we see is we're going to have something that at least Osborne calls beta phi, big phi. Again, depends on GJ. It's R. Well, it's important dependence is only on J. And R here is the scalar curvature again. And then we're going to have a term that looks like this. And we're going to see two derivatives. The reason we're seeing these two derivatives is that power counting is fixing what the form of the anomaly can be, right? And so there's the usual set of rules that goes from having some candidate anomaly terms to the anomalies that are actually realized. And the thing that lets you choose is a consistency condition, which I'll get to, called the Wess-Zumino consistency condition. Yeah, so, well, really, I want to raise this. Right, so there's some structure chi, again, depending on J, which is in the middle. And, well, nothing's to stop us from actually also having a certain term where I have a derivative actually acting on the Weyl factor. So I'm going to have to break this line up, it looks like. Great. And so yet again, we have this. And what we have in addition to the derivative on the Weyl factor is going to be a structure called Wi, which again depends on the source, right? And we're going to see the raised partial U. Yeah. So in a certain strict power counting scheme, these are all possible things you can write down involving no other operators, involving functions of the source times derivatives of the sources and of the Weyl factor sigma. Now, what's done next? So just lay this game out, right? We just start by taking the infinitesimal while variation minus the variation. So we have a definition that the while variation of the source equals a beta function. That's just a definition. And so this is a chain rule variation that depends. This is like a total while variation of the generating function. Well, this would be the total while variation. We're actually subtracting this part. So it's all about this is like the explicit variation, as in the explicit breaking of conformal invariance, and that's all captured by these anomaly terms, right? So that it's like the anomalous violation of conformal invariance is captured by them. Anyway, starting from here, the idea is to think about these things as operators. So really, you want to take. So at least what Osborne does is he takes this and then he defines this to be delta sigma. And then he also chooses to define a second object which knows about the beta functions. And that's the one that we're subtracting here. Right, so there's going to be a beta. Again, smeared by the same while factor sigma. Purpose of doing this is that we can express the basic fact that while transformations commute. This is an abelian algebra that these objects have to satisfy. In other words, we say that delta sigma minus delta beta sigma commutator with the very same thing with a different while factor acting on W should equal 0. Now, that should is going to enforce relations between objects sitting inside these ansatses. And in particular, when the dust settles and we all go remember how to vary the Ricci tensor, we find the following structure. Where V really is, so yeah, see if I write that okay. So it involves partial mu beta I minus partial mu J times beta I, if I'm recalling correctly. And then there's going to be some term that goes like, well, there's some structures like this. And what we'll eventually find, so there's going to be terms that involve the little wi, right? So the structure is little wi. But already at this level, we see that there's the relation, the partial mu beta minus partial mu j beta. So this depends on space only through j. And so this derivative will produce yet another one of these. And then what we're going to have is the j variation of beta, which really, well, okay, yeah, which really we can contract with yet another beta I, right? Well, actually, this is how it actually works. The structure chi was involved all along, so I'm gonna have it here. So for now, if I'm allowed to ignore the dotted terms, which I'll come back to, but for the purpose of the discussion here, we want to ask what conditions v mu equals 0 implies, right? Because that's what the demand is of the variations with respect to while parameters, with different while parameters commuting. And already from this piece of the equation, with the promise that the rest will not matter, and I'll come back to that by going back to the original reference, we see that we can write these two terms as partial mu j, partial I, or is it variation with respect to j that I mean here, ji, or rather the derivative with respect to ji acting on beta. And just if I was allowed to say this, right? So I'll put this in quotes, or well, let me just make this red. That would imply that if I set this to 0 and then multiply by beta on both sides, that beta I partial I beta phi equals I think this should be a plus. I'm not wrong. Yes, I think it should be plus. All of these mistakes shall be corrected once we look at the original reference. So you have a relation like this. Now, beta phi is the thing which at the fixed point becomes c. So it is the stand-in for the flowing c function. This relation here actually defines the derivative, the scale variation of beta phi. That's what we mean. It's flow under the RG. And that is negative definite provided that chi is positive definite. So this is basically the monotonicity condition under the RG flow of the C function, or the flowing C function. And I've done this rather fast, and the precise argument to make actually is that even when we go back and correct this expression, whatever we find here in this relation will be such that when I multiply by beta on both sides, that the rest vanishes. So really, the red equality becomes a regular equality, provided I'm contracting this entire expression by beta j. Yeah, so well, I should do this differently. I really want to drop partial mu j, right? So I'll just put this as k, and then I want to say that I remove these terms, right? These terms, and then dot in beta k instead. So let me just leave that as the caveat equality. But as promised, Osborne's original paper has the right answer. So here we are. His little g is my big J, and everything else is more or less similar. Now, there is arbitrariness in how we're defining W, because we can basically, absorb things by redefining W with local counter terms, but I'll come back to that. For now, let's just go back to the calculation I was trying to do and the terms that I had dropped. The terms I had dropped were basically the beta dotted derivative with respect to what I was calling J of W d mu G. Okay, this was a minus. My bad. Now V equals 0 just becomes the following expression, right? And this is the Lie derivative defined properly with respect to beta. And I guess I was getting that sign wrong, but well, I decided it was wrong later down the line. Or it's basically a convention of whether you put minus here, well, minus here or plus here. Now, what Osborne does is redefines beta with W dot beta. And he notes that, well, in Zamolodchikov's theorem, it basically taken Wi equals 0, which was sort of proved self-consistently for within conformal perturbation theory. But as promised, this equality holds up to something which is antisymmetric in I and J, and so upon contracting with the second beta, we would get the following expression in terms of beta tilde, which involved the stuff that I had ignored, but fine. Now, this, according to Zamolodchikov, is basically the strong C. Sorry, this according to Osborne is Zamolodchikov's C theorem. And again, note that beta tilde is stationary when beta I equals 0, right? Okay, so that's why it goes to being C, what we refer to as C. Now, he says, well, let's actually substantiate this intuition. So what is chi, or what are all these objects? I just wrote a bunch of definitions, and within those definitions, I did this calculation and obtained what I obtained. But he says, look, this equation 12, right, which is the one that we started with, contains concise relations for correlation functions that can be obtained by functional differentiation, which is again what I described by saying that these are all correlation functions in the presence of sources, which then you can pick the source in a particular way. And the way you pick the sources are to take gi, my big Ji, to be constant, and to stay in flat space. Now, in 2 dimensions, the essential content is found by considering just 2-point correlation functions. That is an important point. Because even just to think about the anomaly calculation and inferring the anomaly from correlation functions of the edge momentum tensor, we see that it's a dimension-dependent thing as to what you do, right? So in 2 dimensions, the 2-point function of the stress tensor would suffice, but that won't happen in 4 dimensions and higher. And this is related to exactly the same point that you need to look at triangle diagrams in 4 dimensions to get the anomaly, right? To perturbatively compute, say, like ABJ anomaly. But then as you go up in dimensions, this starts to change. And you're going to need a hexagon in 10 dimensions, for instance. Anyway, coming back to 2 dimensions, what we see is that if we just took the derivative with respect to first the metric and then the source, we get these 2 equations, right? So we have the trace of t equals stuff. Now we're differentiating that with respect to the metric, and so we get the correlation function of the trace of t with yet another stress tensor. And the stuff involved this beta O object that is called theta here. So Osborne calls it theta. So there's a correlation function between trace of t stress tensor minus theta stress tensor. In fact, it's better to just think about this as trace of t minus theta correlation function of the stress tensor equals beta phi, what we had before, times what remains from taking the variation of the Ricci curvature with respect to the metric. And notice that there you have this delta function because you've taken the source to be flat. And you get this, and this is the source of the boundary term for the Einstein equations. And in 2 dimensions, these are the coefficients that you would have. So that's one way to think about it, if you like. Now, when we take the derivative with respect to the source, a very similar story appears. Again, trace of t minus theta correlation function with curly O, which is what you get by differentiating with respect to g. That's the definition. Then on the right-hand side, we have that term that I was disrespecting a little bit, which involved the variation of the Weil factor, of the derivative of the Weil factor and the derivative of j in the anomaly. And that gives rise to the following kind of expression. Perfect. So we have these 2 terms. And further, what we're going to do is see that if we actually defined d in the following way, right? So d is basically now the derivative with respect to what we normally think of as the RG scale, plus beta I times the derivative with respect to g. Then you can actually write Kalan-Simansky equations using what we already have. So basically see that you get that for general stress tensor correlation functions, you get that d acting on that is 0. And you can go and figure out what happens when we have the expectation value of O times the expectation, or the expectation value of OT. And you're going to see anomalous dimensions appearing, right? And then you also have the OO expectation values. And all of this comes from further differentiation. That's all it really means. And so what the point of doing this is to say that you see here, right? So let's look at 19A and B and 20C, right? So let's keep our eye on this ball. Notice that we couldn't access this chi dij term from just looking at the variation with respect to O once of the local RG equation. The reason for that was that you set the source to be constant, and then the derivative with respect to the source of partial g squared dotted with chi is not 0, but then when you set j to be constant, then that term identically vanishes. So you need this term in the boundary to see something just at this level. But then if I take another variation with respect to the source, then I pick out exactly that term. What do I mean by that? I'll just go a little bit more slowly. So here's the structure of the RG flow equation. The game is to look at this, call this trace t minus theta, and then differentiate further w with respect to sources in the metric. The derivative with respect to the metric gives you the two-point function of trace t minus theta and the stress tensor, which is related only to this term. It's the only thing that depends on the metric, which doesn't go to 0 once you take both g to be constant and the metric to be flat, right? So there will be a contribution from here. It's just that when I take g to be constant, these derivatives identically vanish. Same here, it's going to be a contribution from here too. But then when I take g to be constant, this will also vanish. Then I take, instead of the derivative with respect to the metric, I take the derivative with respect to the source g. It's going to be two terms. Only this term will survive, because when I take the g to be constant, right, there's a derivative of the delta function, but then this term will vanish. So in order to extract chi, I need to take two derivatives of this object with respect to the source. And that's why we have the relation here. Right, this relation will know about the anomalous dimensions coming from the derivatives of beta with respect to the source as well, and it'll have this term. So basically you can say that like this equation plus these equations just define what little w, beta phi, and chi really mean. Great. So they say, look, alternative definitions of these objects that arise as a result of the additional divergences present in two-point correlation functions not removed by conventional renormalizations that ensure that O is a finite local operator. Basically, contact terms. Great. Now, here comes the conventional C-theorem derivation, which, if we all recall, is usually done by looking at correlation functions of the energy momentum tensor and the energy momentum tensor and the deforming operator. And here, the choices that Osborne makes is to write the stress tensor two-point function explicitly in terms of its, well, basically in terms of this omega. And then, well, here you have TO, again written in terms of this omega I, and then you have OIOJ written in terms of this omega IJ structure. Now, what we find is a relation between these general functions, which Zamolodchikov uses as well. It's just that he uses slightly different conventions. Ultimately, they would boil down to this, right? He uses a convention where you'd have separate general functions and find relations between them, but ultimately what it boils down to is a dictionary between these functions, omega of x squared, or ZZ bar in Zamolodchikov's notation, and the beta, W, and chi. And finally, Zamolodchikov defines the Zamolodchikov metric a certain way, which, well, is just the following. And that is just given by chi plus the beta derivative of the Cij object, which is like a redefinition of chi. And then further, this lets us also compute W and C, right? So then you see like the C is the equivalent in Zamolodchikov's definition when he uses F, G, and H, and then writes C as the following linear combination of F, G, and H. And H is G, I, J, beta I, and beta J. And ultimately, Zamologic of C, appropriately identified, which again is related to beta phi times W beta, right? Where W is just a redefinition of little w. So there's just a scheme difference between these two. That's ultimately what this is. And I'll comment about these redefinitions as well, involving these coefficients little c. But ultimately, this gives us back Zamologikov's C theorem. So that's the sort of punchline of this entire argument. And crucially, what was used to relate these two schemes was the invariance of W up to the addition of local functions representing like counterterms. When you define renormalized couplings, you have a scheme to choose. And the general kind of redefinition is written in the following way. And basically, you can show using or knowing how R is varied with respect to Weyl transformation, that these are the invariances of the various local renormalization group functions. Chi literally has a tensorial transformation with respect to some Cij, right? So there's like the derivative with respect to beta of Cij. So this is really transforming like a metric. W has an almost vectorial kind of transformation, but not quite, because there's C and little b, but little b is also related to beta, right? The variation of beta, which means that there's some combination of W and beta, and well, or W and beta phi that actually transforms like a nice geometrical object. And well, that's what beta tilde is. So the reason I wanted to come back to this is first why you see here you can write the Samologikov metric as some gauge transformed chi or redefined chi. And similarly, you can redefine W in the ways you're allowed to redefine it, and beta phi. So this is like beta tilde. That's what gives you C. So there's a sense in which you have an invariance of the renormalization group under certain redefinitions, which is very much akin to the kinds of invariances and subtleties that were being referred to in this abstract. And they also play a key role in the actual sort of Zeitlin way of thinking about the renormalization of sigma models and how they kind of know about things like target space diffeomorphism invariance. Because those are just, they're those kinds of transformations from the perspective of the world sheet. It's kind of hard to see otherwise. Anyway, this nice paper goes on to discussing four-dimensional field theories, comments on things like the A theorem and so on. There's just a lot more invariances to deal with. The anomaly grows much bigger. And well, there's commitments to specific models to kind of derive some perturbative results as well. So it's a very good paper, and I highly recommend people reading it. Anyway, I hope you enjoyed this discussion. As I said, I'm a big fan of these methods, partly played a key role in my own PhD. And I hope to catch Amar and Aaron at some point to talk to them on this podcast about their new paper. So if either of you are hearing this, please join. And if you've come this far, like, share, comment, subscribe. It really helps the channel. And I'll see you again on yet another episode of Theoretically Podcasting. Thank you.